So now that we have proven the relational naturality law, we need to do some more work in order to be able to use that law more effectively and more easily. In most cases, when reasoning about functions, one does not need to go to the full generality of the relational naturality law. And that law is quite complicated in some cases because it has arbitrary relations and not functions. And so there must be some shortcuts if we are to derive equations with functions. And the shortcuts are based on deriving what's called the wedge law. And the wedge law is a generalization of naturality law for type signatures that are not covariant, not contravariant. So I will show now how to derive the wedge law, and then I will show how to derive naturality laws. Naturality laws are the most often used in practice. So once we derive that, it would mean that we have proved that all fully parametric code of a specific type signature will automatically satisfy the naturality law. So the first step is to derive the wedge law, which I will formulate. And this derivation is based on this blog post. And that blog post is not very easy to follow, but I try to make it more explicit and spell out all the details. So what are we going to prove is that for any function from f from a to b, and for any fully parametric profunctor, which is a type constructor, contravariant in x and covariant in y. So this profunctor has methods CMap or contramap of this type signature and fmap with this type signature. So the CMap changes the first type parameter, but it goes in the opposite direction. And fmap changes the second type parameter, mapping with the function f. And then you have a fully parametric value of this type. So for all a, PAA. Now this is, I explained in earlier parts of this tutorial that when you have a type expression that is neither covariant nor contravariant, you can rename contravariant positions and get a profunctor such that your initial type expression is this profunctor with the same type parameter put in, but then it's much easier to deal with that type because you have covariant and contravariant positions separated. So this is what we will do. And the wedge law is this equation. Now, this equation says the value t applied to type A and the value t applied to type B satisfy this equation. So for any function f, for any types A and B. That's a pretty general law. And the diagram for types in this law is that we begin with two arbitrary values of types P of AA, P of BB. So these are not actually arbitrary. These are t applied to A. So this is the same value t, which is applied to the type parameter A. It has this type. And the same value t applied to type parameter B, it has this type, must satisfy this equation. So when you transform this with fmap, then it gets you to some value of type P of AB. And when you transform this with CMap, it also gives you a value of type P of AB because B goes back to A here. And so those two values must be the same. Now this seems to be a strange law. Why would you want to use this law? And the reason you want to use this law is that this is a generalization of a naturality law for type signatures that are not fully covariant or fully contravariant. I'll show from this that we will derive naturality laws. So how do we prove that this holds, this equation holds? Well, we use the relational naturality law, but it's not easy to use it at this point because we have two different functions. So the relational naturality law is a law saying that the same function with different type parameters satisfies the law, but we don't have the same function. So we need to make them the same function. And the way to do that is to go to this cross-map function. The cross-map function is a composition of C-map and F-map, so that the cross-map function has two functions, and at the same time, it can map both type parameters of a profunctor. So first it maps the contravariant type parameter, and then it maps the covariant type parameter. So if we define X-map like this, we just define it like this. And from the earlier parts of this tutorial, you know that for any profunctor P, we have standard unique code of C-map and F-map, which is fully parametric, which just follows from the type expression of P. And so the composition is also going to be some fully parametric code. And then obviously this expression is just written like this, because F-map is X-map where you have identity instead of G. And C-map is X-map where you have identity instead of F. So then we have this equation that we need to prove. That's the equation we're going to prove. And that is now in the form that the same function with different type parameters is equal. So that is some hope that so now we have some hope that we can use the relational law to prove this. Now, earlier I mentioned that there is a commutativity law for this function cross-map. And the law is that first you could lift contravariant and then covariant, or you could do it in the opposite order, and the results should be the same. Now, we have not yet proved that the commutativity law holds, and the commutativity law is actually a naturality law that we're trying to prove. So we cannot use that law right now at this stage, because we're still trying to prove that naturality law holds. And the commutativity law is just a naturality law written for these functions. So we're not going to assume that. We're just going to say, let X-map be equal to this composition in this order. And it's perfectly fine, because we have these identity functions. We don't need the commutativity law to express our equation in this way. We're just going to say, well, this is this function, which is this particular composition, and it is fully parametric, therefore. So the relational naturality law holds for this function. So let's write down what it means that it holds for this function. It's a quite complicated law because this function has 4 type parameters. And that means we need 8 different types, 4 different relations between these types. And then we need values. So we need also a lot of values here. So 6 different values for arguments. And then we can write down the relational naturality law. So we're going to introduce this notation: AA prime, BB prime, XX prime, YY prime, P, Q, R, S. They're going to be relations. And then functions F and G, FF prime, G, G prime. And then V for this and V prime for the other one. And then we say, well, if FF prime is in that relation, GG prime is in that relation, VV prime in that relation. Now, notice here we need simultaneous lifting of S and P in order to represent this part, because it has 2 different type parameters. Then the values of the X-map function are in this relation, which is lifted. So the R and Q, right? So R replaces X, Q replaces B. So that is going to be the naturality law. the relational neutrality law. This is quite horrible. What we need is to get the equation from it, this equation. So it means that this last step must be an identity relation. So this must be an identity relation. Then we'll get this equation from it somehow. We will certainly need to substitute f, g, f prime, g prime, v, and v prime in specific ways so that we reproduce these values here, which is what we're going to do now. So how do we get an identity relation? The trick is that we need to know that when you lift identity relations, you also get an identity relation, no matter to what you lift. And that's a special property, that lifting an identity relation always gives you an identity relation. And so you choose the identity relation for R and Q between x and x. So we have to choose x prime the same as x, b prime the same as b. And then this gives you the identity relation of this type. So this is a theorem, actually, or lemma that you need to prove, that when you lift, or even this simultaneous lifting also gives you identity relation. And when you prove that, you go, again, by induction over all the cases. I'm not going to show you the proof of that. I have this in my book. This is technical, but you also need to prove, for example, that when you lift simultaneously two relations and one of them is identity, then it's the same as when you lift only one with respect to a type parameter while keeping the other type parameter fixed. So that is, for example, let me illustrate somehow. If you have a type constructor f of AB, and you have a relation R between A and A prime, and you want to lift R map to R ID to F, then this is going to be a relation between F of AB and F of A prime B. So you keep B fixed when you do that, so to speak. Now, you could just say, let's keep B fixed. Let's define a type constructor G as just F of A B with, so G of A, let's define G of A as F of A B. We're keeping B fixed. And then let's just lift to G of A. And that's going to be this lifting. And consistency then requires that it's the same result. When you lift identity here, you get a relation between these two. Or if you lift just R to this G, then you also get a relation between these two. That must be the same relation. So this you need to prove also by going over all the cases in the definition of RMAP. So now I'm not going to show you that proof because it's really straightforward. You go through the definition of relational lifting, simultaneous relational lifting, and you put identity. In every case, you get identity quite straightforwardly. So for example, for the function mapper, if the two arguments of a function are equal, then the results of the function must be equal. And that means the functions are equal by the usual definition of functions being equal. So that kind of thing works for every case, for tuples, because they're equal when each part is equal, and so on. So imagine now we have proved this, and so then we can just choose R and Q as identity, and we get here the identity relation. But actually, to prove that identity extension lemma, or to prove this that lifting is giving you the right results, you also need to assume full parametricity. I'm not going to go over the details, but essentially there is a technical detail that you have to assume parametricity, and you have to assume that the parametricity theorem holds, and apply that theorem in order to show that this is right. But we already proved that theorem, and we did not use the identity extension lemma, so that's fine. Now, the next step is that we have this kind of equality. Now we have substituted some things, and what we need is, however, this. So we need to choose these values like that, so that what we need comes out of the relational law. So this is the relational law that we have proved. So let's choose those types and the values accordingly. So then we get the law that we need. However, this law has a big precondition. All these things must hold. F and F prime must be in this relation, G and G prime must be in that relation, and so on. V and V prime must be in that relation. And we need to verify that all of that holds. So let's verify. So then F and F prime is identity, F is an arbitrary function. So F identity must be in the pair function mapper of P and identity. And that, if you write it out, it means for any X and Y in P, F of X must be equal to Y. Now, how can that hold? Only when P is the same relation as this. So P must be the graph relation of the function F. Then this will hold. Okay, so that means we choose P as the graph relation of the function F. So far, we did not choose P in any way. Similarly here, we have to choose S to be the graph relation of the function F. So if we write out what that means, then for any X, we need X of F of X in S. So that is a graph relation of function F. And for the V and V prime, if we write it out, it means V and V prime are these. So TA and TB are in this. Now S is equal to P. We already chose S and P, so we have no more freedom. Now we have a double lifting, essentially R map to a P of P and P, or S and S. S and P are the same. Now, this is not, so what we need is a lifting to the type that we had initially. So this type, the type of T, let's see, P of AA, right? So what we need is the lifting to the type constructor F defined like this. That is actually the parametricity law of T. We do not have that T of A, T of B are in that relation, are in the relation R map 2 of PP or SS. We don't have that. We have TA, T2, TA, TB in R map F of P. That's what we have by the parametricity law. So that's the assumption for the expression T. So we need to prove that that's the same. In other words, if you have a type constructor F of A, which is expressed like this, then you can lift a relation between A to B to this F to get a relation between F of A and F of B. Or you can lift a relation with respect to both type parameters at once using the simultaneous lifting operation. That also gives you a relation between P of AA and P of BB, which is the same as F of A and F of B. And these two relations are the same. So we need to prove that. That's a lemma that you, again, have to prove. That's a technical result. And this technical result is proved by induction over the cases. I'm not going to show you the proof, it's in my book, where you also need to prove that the simultaneous lifting of 3 relations, where 2 of them are repeated, is the same as the simultaneous lifting of just 2 relations to a type constructor where the 2 type parameters are equal and collapsed into a single one. So that kind of proof, you have to go through all the cases and prove that this is true, and then you're done. And this is quite straightforward. There are no tricks that you need there. You just go through all cases. With all these choices that we just had here, the relational parametricity law for T, which is this one, reduces to the wedge law, which is this equation. Now, suppose that the type signature that we have of T is this. So suppose that we have T of A of type G of A going to H of A, where G and H are both covariant. Then we define, now we rename the contravariant position. This is going to be a contravariant position because G is covariant, it's behind the function arrow. So we rename this to X and rename that to Y. So we have this proof functor for which we use the wedge law. The wedge law will look like this. And then if we write out what F map P and C map P are, then you get this for this function type. So then the wedge law is written like this. And that's exactly the naturality law of T, telling us that T followed by F map is the same as first doing F map with this and then following it by T. So that's the derivation. That's pretty straightforward. The naturality law for type signatures where both of these type constructors are covariant. And similarly, the derivation goes for contravariant, both contravariant. So this finishes the proof that fully parametric expressions and fully parametric functions satisfy the laws that we have written. There's a very general law, the relational naturality law, but for specific cases, we have an ordinary naturality law that follows from it. And then we have the commutativity laws and all other, and unit lemma and all that. We just can use the naturality law directly. It's much easier to use a naturality law than to go back to a relational law, write out all those conditions, try to substitute relations in the right way, function graphs or some other relations, and so on. So naturality laws are a shortcut, and whenever possible, we will try to use them. So I showed in the tutorial that in many cases you can use naturality law, for example, for the unit lemma, and then you have a lot of results derived very quickly, and you don't have to go to the full relational parametricity law. But in the next part of my tutorial, I will show cases where naturality laws are not enough, unit lemma is not enough, and you have to go to the full general relational naturality law. That is going to be the advanced examples that illustrate the use of relational parametricity in its full power.